section 2.1, we talked about average rate of change, and we talked about specific instantaneous rate of change using the difference quotient when only 1 point is given. As 2, we could possibly have a secant line. Everybody understood that on that particular section. We also dealt with speed, and speed is a natural course of what we do in our vehicles. If we're on the highway, we're looking at 70 miles an hour, right? And if we're in the burb, we're talking between 25 and 30 if it's my burb, because I mean, it's, a lot of houses. So, so we're going to continue to work on limits. And this is going to some point C. And that the C is used because we have a domain of where we're looking from A to B, and somewhere in between is a C. So that's where the C comes in. This is reference to that particular point. It is a number because it's a lowercase letter. It is a number, okay? Okay. So we're talking about something that is described. So we have this rational function right here, y equals x plus 4 over x squared plus x minus 12. What happens at x equals negative 4? Well, in Algebra 2, they told you to immediately do the F word to find asymptotes, right? So what is the F word? Yes, factor. So let's look at it algebraically before we look at it numerically. Is that okay with everybody? So we're saying here that we've got y equals x plus 4 over, and I'm going to factor that, and it's going to be x plus 4 times x minus 3. So if I cancel this, then this is a what? Not an asymptote. What is it? Algebra 2. It doesn't exist at that number, but it's not an asymptote. What is it? Hole in the graph. Exactly. It's a hole in the graph, and we call it a removable point. I can't spell. Can't talk English and can't spell. You've got a great instructor. It's a hole in the graph. Right. So we've determined that it does not exist at 4. Now we're going to measure if this is a limit, because even though it's a teeny, okay, there's that concept that you can take a half and a half and a half and a half and you'll never meet. That's this concept here. Does it almost touch this point at whatever value we have? And the value would be 1 over 1. 1. Something like that, ridiculous, or whatever this thing is. All right. So now what we're going to do is we're going to use our grapher and enter this rational function. And make a table. One of the stronger things that we can do for calculus. I'm going too big. Come on. Go. I apologize. Anyway, let me try to do my best. Okay, that's the best I can do. All right, so we're going to erase whatever we have. And we're going to enter the argument in the numerator in what? What do we enclose it in? The argument in the numerator, parentheses, and the argument in the denominator in. Otherwise, it'll only take the first term. And on the top, it'll take the second term to make fraction in the whole thing. Okay, so we're going to put open parenthesis, x plus 4, put in all the arguments so we can visualize the whole at that value. Divided by, open parenthesis, the x squared plus x minus 12. Okay, did everybody get that? Okay, we want to do zoom 6. Standard window. Bam. Okay, so it looks continuous at 4, right? And we know the asymptote is at 3 because the factor was over x minus 3. So we know that. And now let's just go ahead and put in, or see what output we have. I have 1. Was it 4? Negative 4. I'm sorry. Negative 4. I apologize. Negative 4. Your instructor. All right. It has no answer because it is a hole. And the graph will not show the hole unless you go really into it. So what we're going to do is the table around it. And the closer we get to 4, the more accurate our limit is. So here we go. So we're doing our second calc value, negative 3.9. Make sure you use a negative. And I get a value of, it looks like negative 0.14. 144. Did you all get that? Okay, just making sure that I'm on point. 3.99. Getting closer every time. Negative 0.14. Well, actually, it's just another 4. If I round it, I'm going to say 3. 3, it's a 4. Negative 3.999. I get a negative 0.143. Now I can't do 4, so I'm going to do negative 4.001. Negative 0.143. All right. Then I'm going to do, now I'm getting further away from that point because I have to do the left and the right. And that's the whole point of finding a limit. And it's a negative 4.01. I'm getting further. Now I'm getting larger. And then I'm going to do the negative 4.1 and I get the 5. It looks like a 5. So we can see that between these guys, they are almost paired. We'd have to do more decimal places to see the variance. But we would definitely say the limit is approaching negative 0.143 from both, like 5 decimals to see that variance. And we can do it by the table. And this is another thing that we can do. We can do second calc and to the window, second window, sorry. And we want to make sure that we ask. It has to be on ask. So we can go like this, have ask. And then we can go second graph and then enter all of those values and get the same thing if you didn't want to do the window. And on this guy, you would have to highlight the other side to see all the decimals. But for me, this works better because it's a larger font. But any way you want to work these are good to find limits. But that was just telling you what a limit is. It doesn't have to exist, but it must be coming from both sides. Now, is there a limit at x equals 3. No, the reason that we don't have a limit at x equals 3 is because before 3, which would be our second calc trace, we would have said 2.999, right? Because it's a positive. Okay, so we're going to do 2.999. That's on the left side of 3. It exists. So we'd hit enter, and we get this giant negative number. It's actually 1,000. Okay, so we know it doesn't exist at 3. So what about 3.0001? Sure, I put it in. And I jump up to what? The positive 1,000. So they are not coming to a consensus like we did on that negative 4. Is everybody comfortable with that? All the algebra you did is for this jump right here. Understanding that we've got a hole, understanding the difference between them. Yes. Yes. Can there be a limit on an asymptote? No. Okay. And I already did it mathematically. I did it first mathematically, is to factor to figure out that it is a removable point. And then, so what do you see as a limit? And we did. We estimate. All right. So here is a piecewise function. Piecewise. Piecewise means that things change depending on specific domains. And you can have many more. Does it happen in the real world? Yes. Do I have an example? No. But engineers do. So what do we know? We know that this is a domain of negative infinity to, well, if we just did them as segments, it would be from, well, I'd say -2 to 8 if it was dots on the bottom. But I can't. So we know it's negative infinity to infinity as the structures go this way. And where the removable point is, we have a specific outlier that pulls everything out. And this guy is on this line, so that is definitely interesting as well. All right, does everybody understand the graph? All right, we're just naming stuff. All right, here we go. This is an example of a graph, and it wants to find the limit as x approaches 2. Now remember, for a limit, we have to go from the left and from the right. So 2 is right here. Okay, if we go from the left, it says from the left, there's a minus that you put up there, it is like 3. If we did it from the right, it approaches, it's a plus, it approaches 0. Does everybody see that? Are they the same? Or approaching each other? No. It's approaching 3 there, and 0 does not exist. Ever comfortable with that? But we do know that f of 2 is 0. That bearing is only if we want to go on one side. For this section, now we're going to get real technical. It really gets technical in a minute. But this is just visual and understanding. Well, what about if it reaches 4? What do you think that is? What is the limit? Because from the left it's approaching 2, and from the right, it's approaching 2. Is everybody comfortable? And it's continuous. The idea of continuous is critical in calculus. Continuity is critical. And now this is a cusp, because if it goes to a peak, it's called a cusp. So you know when I say it again. All right. Now we want the limit as x approaches 6. What is it? Yes, it exists, even though it's a removable point. Even though f of 6 is 5. The limit is that both of those lines are headed toward 0. And they're continuous before it and after. Good point. I like that. Everybody, okay. What about 4.5? We have a limit. Yes, we have a limit. It's approximately like 1.5 or something, or yes. Yeah, and it'd be an approximation. It does exist. That is on the line itself, and therefore it exists. All right. Now, this guy right here is always an issue. Why is this one an issue? What's a domain restriction here? Yeah, so what can it not equal? 0. X cannot equal 0. And then we have the added problem that it's an absolute value. So it means that the negative part is only affected if we have the x on the top. In other words, can I say this is always 1? No. It is -1 on the negative side, doesn't exist at 0, and then it's a +1 on the positive side. Like this, I think, right? So we know it doesn't exist there, right? So it would be a -1 till it got to this point. Then it would be a +1 this point, and nothing in the middle. I think. Let's do it. Heck, I don't know. But so we're going to put our x, and we're going to hit the divided. The absolute value can be gotten under the math key, or it can be done under catalog. So I use the catalog, the 0, because it's the first one. On math, it's like the third one or something. So I'm going to go zoom 6 so it looks pretty. Okay? Everybody see it? All right. So everybody got an idea now. You have an expensive tool that I make you buy. Use it. You've got, as an engineer, you have to visualize all of your functions. That's what you do. Somehow you've got to tackle that, the impossible areas as well as the possible areas. And in engineering, you focus only on what you need. The limit of how many people you need is that limit. I told you that. So it doesn't matter that it collapses after, but if we can keep it right there, that limit, we're good. But visualization of what you're looking on is important, especially on continuity and domain. So here are some rules of limits. Don't write them because I'm going to post them. And they're logical. These are logical. Please, it's arithmetic. Arithmetic. If you keep that in mind, you won't make it. That the sum of the individual terms of a function give you the limit. In other words, you have an argument plus another argument. If you do them distinctly and add them at the end, you still have a limit. Okay? That's in a complex functions. You divide them. Same with subtraction. The K. What? What does K mean here? Well, it's a constant. When we do antiderivatives or even derivatives, we pull constant out because it's just an amplitude or the impact to that. But we can do the action here and then multiply through, and you're fine. Keep it simple, stupid, right? Okay, that's what that one is. And then the LM is, again, if it's factored, you can do this limit and just multiply rather than do FOIL and then do the whole thing. Does that make sense? All right. And division, only the G is restricted, G of X, which is in the denominator. Oh, now this one's good. And that is, don't do exponentials till the end. That's what it says. Do the limit inside and then do the power. Okay. And the radical is the same thing. Now we have to know that if I have the X, this is X to the what? That's why it's not a polynomial. If you have a fraction on a polynomial, it is not a polynomial. It is a root value of something. So, and you want to get rid of the radical because this is easier to take a derivative on. Much easier. And that's what it's saying here. Go ahead and change it, you know. So we want to find the limit as y approaches -7. Now, the first thing is we don't have to do the difference quotient. We don't have to do anything. We just want to know if it exists. Is there anything that stops it from existing in the reals? Okay. Analyze this guy right here. What is this guy right here? The line. Is there any restriction to a line? Will a number exist for any point of a line? Yes. There's going to make it ugly. Therefore, I can drop it. Drop in the value. So I'm going to have 1 minus a -7, correct? And according to the rule, we do this guy first. So that's going to give me 8. And we know this guy right here is 2 to the 3rd, right? So 2 is the base, squared is 4. What if it's just, you know, I get anxious doing it by hand? What can you use? Thank you. Everybody put 8 up caret in parentheses 2/3. Everybody. Don't trust me. I'm bad on math. I didn't bring my spares. Next time. And color grade on that. Did I get the same thing? Okay, we're good. Just making sure my math is good. Again, here we have the limit structure of what we did before in a sense, because we have an H. And so in order to do this, we know that H cannot equal 0. So therefore, we're going to manipulate, and we're going to do multiply by conjugate. Does everybody remember that? Okay, I'm going to help you. Now, multiplying by conjugate only works on rational functions because you don't want to change anything in its value. You want to manipulate it so that you can derive where it functions. And what we want to, and we know that at 0, It might be a whole or it may be an asymptote, but we're going to find out how close it is. And we're assuming some things because it only told us to do the limit. All right, so this means that if I have 14h plus 1 to the 1/2 minus 1, and this is my argument, and I'm going to multiply by conjugate. That means same terms, opposite sign. Ready? Same terms, opposite sign. But I'm going to multiply both the numerator and the denominator by that value, because I can multiply by 1 and not change a thing. Oh, it's a plus here. Sorry about that. And we still have the h. No fears. If I multiply by conjugate in the top, okay, think about it like this. So if I multiply the square root of 5 times the square root of 5, I get 5. And that's what we're doing. We're multiplying, okay, but we're doing it with FOIL involved. All right, because of the -1. It's a 2-term. But what we're saying is, booyah, it's going to come out of that radical. All right. So when I do this math, I'm going to end up, now remember, this is the limit as h approaches 0, so please don't think I have forgotten. I'm going to have 14h plus 1, and it's going to be minus 1. How convenient, right? Square of the first times the square of the last, minus, because it's a conjugate. And then I'm going to have h times that mess. Now we don't care that it is a 0, because we're going to cancel out the h, the major h. Sorry about that. All right. Okay, so this right here are additive inverses. Everybody see that? Okay, so they're gone. All right. So I'm going to have 14h over h times 14h plus 1 plus 1. Like that. There's two parentheses there. Okay, what happens with that h? Cancels by factoring, right? They have the same factor. All right. So now I'm taking the limit of that as h approaches 0. So I'm going to be left with a 14 in my numerator. This guy right here is 0. So I'm left with 2. A 1 plus 1. Does everybody see it's a 1 plus 1? 2. So what's my limit? 7. Remember the conjugate? It's how to get rid of a nastiness. Usually we call it rationalizing a denominator. Would work out pretty. Yes. All right. Now we have x approaches 19 of x squared minus 361. And we know from this guy right here, that we've got some kind of perfect square. So we're going to guess it's a perfect square because they wouldn't give us a problem that wasn't, right? So I'm going to do the square root and verify that 361 is something we can work with, and it is. So we can factor. And we understand that at 19, it's a whole. If x is 19, it's a whole, not an asymptote. So therefore, we can take the limit. Does that make sense? You're looking at me weird. What did I say that doesn't make sense?
I'm sorry.
Sorry?
How is that an asymptote?
Oh, because we cancel it. If I cancel it, then 19 is a whole. I can tell you that. If I put in 19 in there, it's 0 over 0. So I factored it, but we know that x cannot equal 19s, but it is, we can prove then that it's not an asymptote because I canceled it out. Of course, you can graph it, whatever you want to. This one's busy, so now we're taking the limit as x approaches 19 of 1 over x plus 19. And that's going to give me a value of 1 over 38 if I did the math right. Snazzy, right? At x equals 19.
19.
Yes.
It's the what cancels out.
What cancels out is a removable point. If it doesn't cancel out, it's an asymptote.
Positive 19 because you have to say equal.
It has to be 0 in the denominator. Once you obtain a 0 in the denominator, now mind you, for this guy, x cannot equal 19 or negative 19. Okay, but the 19 was the one I was concerned with, that I could prove it was a removable point. Good questions. Am I clear? Right. Well, this one, I know this is 13 on the bottom, right? Plus or minus 13. So we know in our domain, x cannot equal plus or minus 13. Okay, so now we have to figure out what they want. Well, they want positive 13. So we're going to factor and see if it's a removable point. On the top, it's got to be 13, right? So I'm going to go on my handy-dandy calculator and go the 182 divided by the 13 and see if it's possible. It sure is. All right, so I've determined by doing this a gazillion times. If I find one thing I can factor perfectly, then I figure it's a factor of the top as well. All right, so here we go. We're going to factor the top. And this one is 13 times 14 plus or minus. So I'm going to have t, and I need it positive, plus 14 times t minus 13 over t plus 13 t minus 13, because it's a difference of perfect squares. Is that confusing to everybody? And of course, I'm taking the limit as t approaches 13. Well, I mentioned that we can't have 13, but the only way I'd have 13 operate as a 0 is if it is input to the original. I would have 0 over 0, which is an indefinite. So in this case, it cancels. So because it cancels, then I know it's a removable point. Okay. Everybody better? Am I saying it more clear for you? Okay. So now I'm doing 13. So this is going to be 13 plus 14 over 13 plus 13. And that gives me 27 over 26. And I can't reduce that because 26 is 13 times 2. The limit is there. How can I check? calculator. All right. We're finding the limit here as x approaches 0. Well, x cannot equal 7 because then I have a 0 in the denominator. So I've got an issue here where x cannot equal 7. It cannot equal also 0 because it's in the denominator in that bottom. Y, and I'm sorry. Okay, so let's look for the LCM. What is my LCM? Right? And we're going to multiply the top and the bottom by 7y. All right. See what happens. If I can do it, I don't know. So on this guy here, I'm going to have 7. For this guy here, I'm going to have minus y. On the bottom, I'm just going to leave. Well, you know what? Yeah. Keep, change, flip. Ooh. Let me do them individual fractions. Because this will factor to this with a negative symbol. Get back. I just want to make common denominators. So this is going to be 7 over and minus y over 7y. On the bottom, I have y minus 7. All right. Now, here's what we're going to do. Because this still cancel that guy. And we can do 7. So when I do this guy right here, I'm going to put it in standard form. So that's going to give me a negative 1 times a y minus 7 over 7y. Is everybody comfortable with that? Okay. When I do that, I'm going to multiply by the reciprocal of this guy, 1 over y minus 7, because it's a complex fraction. So when I do that, these guys what? Cancel. And then I'm going to end up with the limit as y approaches 7 of negative 1 over 7 times 7, negative 1 over 49. Slick, right? That is so slick. Okay, in this case, we don't have an issue. Why don't I have an issue? 269 does not affect the radical. I'll have a real answer, right? It might be an ugly answer, but I have an answer. And it'll make a numerator. So what's my limit? Because it'd be 0 divided by a number. It doesn't matter what the number is, it's going to be 0. Again, recognition is king. That's, oh, trig. Oh, yucks. All right, here we go. All right, we know on a secant, it's the reciprocal of what? Thank you. And cosine at 0 is 1, isn't it? Right? Right. And the secant, this is the reciprocal, right? This is, secant is cosine. All right. So at 0, we have x over y. So it would be 1, right? Secant 1, 1 over 1. This is a reciprocal of cosine. On this guy here, I have to draw it just to make sure I got it. I'm sorry. Okay, on this guy here, we have sine x at 0 and cosine x at 0. Well, this is 1, so we're good. Are we good? All right, this guy is negative 2 pi. Well, negative 2 pi makes this 0, and we're safe. This is 1. So at negative 2 pi, and because we don't know, I can't write. Oh, you know what? It's out of juice. I didn't bring my other one. Okay, I did another one. Okay, so I would insert the negative 2 pi plus 11 times the 1, right? Because that would be 0. And so that's my limit. I think that's it. Yep. All right. I needed these. If you haven't turned them in, please do so. We did great because I'm on point. I finished all of week 1. I didn't do it in pre-count. They were all nervous. For responding, thank you for making me more conscientious. I appreciate that. I'll try to hang up everything. This probably by Friday.